In the previous class, we have learned in this current electricity part 1 that the first 7 points that we have discussed in the previous class, and for today we will try to learn the remaining 8 points, starting from 8 points to this 12 point. That means color code of a carbon resistor. This is a very small, simple, easy topic. And the second one is series and parallel combination of resistors, which you have already learned in your class 10. The next one is EMF and potential difference of a cell, internal resistance of a cell, and lastly we will learn about series and parallel combinations of cells. Now for a color code of resistors, this resistor rather this is a cylindrical small piece of rather material, and on it you will find some circular rings on the body itself. Okay, and out of these 4 circular color rings, you will find 3 of them little bit closer to one another and the 4th one little bit farther away. So these 3 which are very close to one another, these will give you the numeral value of the resistor, and the last one, the 4th one, will give you what we call as tolerance. So let's try to find out the value of a given resistor by observing the different colors. Okay, so the first color, we call it this first color. Whatever those 3 colors which are very much closer to one another, that will be treated as first, second, third, and this the farthest one out of the 4, that we will be called that ring as tolerance, right? So your this will be the first ring, then second ring, then third ring, and then this one will be the 4th one. Okay, so the first ring will give you the first digit of the resistor. The second one, the second color, will give you the second digit. Okay, and the third one will give you the multiplier. Okay, the decimal multiplier we call it, right? And this 4th one will give you what we call as tolerance, right? Now let's try to know what is, if this color is brown, then what will be its value. If it is violet or red, whatever it's what this color represents the value of that color. Okay, let's try to find out that value. Now these are the letters, okay, that represents here with to represent what the different colors. Okay, and these are the actual color, and these are the number to be represented by these different colors. Okay, and in the case of tolerance, it will depend upon the color. There will be only 2 colors. Okay, gold, silver, and this one is having no color at all. So you can have either 2 or 3, you can say, but the color will be only having 2, either gold or silver. And if you are not having any color or the 4th ring, then you need to know that that is for 20% tolerance. Now black will represent 0. Now this color, okay, you will start from the very dark color to the lightest one. So your dark color is black, so starting from the black, it will go lighter and lighter, and it will go up to white. Okay, so black will represent 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, and white 9. Okay, just to remember these colors. Okay, I am having one mnemonic here, and that mnemonic is what? B Roy. Okay, ROY, Roy. BP Roy, BB Roy of Great Britain has good wife. You can remember, has very good wife. Okay, you can remember in that way. BB Roy of Great Britain has a very good wife. Okay, or you can omit that A also. Now the letter here written in capital letters, BV Roy. This B also started with a capital letter, ROY, that is so started with capital letters. OP is not starting with capital letters, so we have to leave this. Gret, G, starting with a capital letter. Britain, B, started with capital letters. Barry, this also started with a capital letter V. Good, G, started with capital letter. Wife, W, started with capital letters. So these will represent what these capital letters will represent, the different colors of the ring, and it will start from 0 to 9. So B, black, will represent 0, brown will represent 1, R, red, represent what, 2, O represents orange and it will represent 3, likewise yellow 4, green 5, this is blue 6, violet 7, gray 8, white 9, like that. So starting from 0 to 9, that means in total there will be 10 colors, right? So let's see how the value will be calculated by knowing the different colors of the ring on the body of the resistors. Now this is brown. The first one is brown, right? Brown, violet, black. So brown will represent what? 0. Brown will represent 1. I'm sorry. Brown will represent 1. Violet will represent what? 7. And then black will represent 0. So if it is like that, then what happened? It will be brown represent 1, violet would represent 7. So this will be the first 2 digits of the what, resistor. Okay, the value of the resistors. So brown will give you the first digit and violet the second digit. The second color will give you the second digit. Okay, and this third color or third ring will represent what we call as tolerance. So as it is 0, 10 to the power 0, 10 to the power 0 is 1, so it will be having only 17. And this fourth ring will represent what? Tolerance. And if this color of the fourth ring is gold, then you will have as 5%. If you are having that color of silver, then it will have 10%, and if you are having no color, then it will be of 20%. Got it? So as this is gold, so you will have 17 into 10 to the power 0 means 1. So 17 into 1, so 17 plus minus of what? 5%. Why? Because this is gold color. Okay, likewise if you are having that of, suppose the first color is green, red, blue and silver, then you will have as the first digit green, means what? Green, for green it is what? 5, right? And for that of red, we know that it is for representing 2, so it will be 52. First digit 5, second digit 2, like that. Okay, and this is what? Blue. Blue represents 6, right? So the multiplier is what? 10 raised to the power violet. Blue means what? 6. Got it? And plus minus, see, this is silver in color, the fourth ring, so it will be of 10%. Now in the third figure there is a slight mistake here. As I am writing here 52, it should not be 52. Okay, it should be 17, because brown represents 1, violet represents what? 7, as it is done here, right? So this will be, instead of this 52, it should be what? 17. 17. Got it? So 17 into 10 to the power 0, because this is black and there is no ring at all here. No ring. So no ring means what? The tolerance should be of 20%. No color means no ring. Okay, so it will be of 20%. So you will have 17 plus minus of 20%. That must, okay, resistance will be there. So that is all about this color coding, and the formula you can see here as like this. A represents the first digit, the first color. B represents the second digit, the second color ring. and C represents the multiplier, the third ring, and D represents the tolerance. Okay, and tolerance will give you about this gold, silver, or no color, right? So if you have that here A, B, C, and this D, then you can easily find out the value of the given resistor. Okay, this was wrong, as I told you that this should be what, 1 7 into 10 raised to the power 0, so it will be 1 7 plus minus 20%. Okay, that much ohm, right? So let's go to the next one, and this is about the another model of knowing or representing the resistor. Okay, in this model, what happened, this is seldomly used nowadays. So you will find this as a colored body. Okay, the cylinder or the resistor will be colored, and the color of the body, you need to see the color of the body, you need to see the color of the two ends of the resistor, and you will also see the dot mark on the body here, and the ring. Okay, the color of the ring, you need to see it. Got it? Yes. First, this also similar to the previous one, the color, okay, on the body, the color which is yellow, that will give you the first digit, and the color of the two ends of the resistor will give you the second digit, and the dot, the color of the dot, I should say, the color of the dot on the body, that color will give you the multiplier, and similar to the previous one, the ring will represent, the color of the ring, I should say, will represent what we call as the tolerance of that particular resistor. So in this diagram, what happened, yellow represents 4. Okay, the color of the body is yellow, so yellow will represent 4, and then the ends, the color of the ends of the resistor, that is red, so red represents 2, and this, the color of the dot on the body, that is blue, so it will represent 6. So 42 into 10 raised to the power 6 plus minus tolerance is gold, so here it will be 5%. So it will be representing 42 into 10 to the power 6 plus minus 5%. Okay, that much ohm will be there. So this is also another one. Let me repeat it again. The color on the body will represent the first digit, the colors on the two ends of the resistor will give you the second digit, and the color of the dot on the body will represent the multiplier, and the ring, that will give you, I mean the color of the ring will give you the tolerance. Okay, and now let's quickly go through that of combination of resistors. Now if two or more resistors are connected one after the another, then that type of combination of resistor, we call it as what, series combination of resistors. So your R1, R2, R3, these are different resistors, and these three different resistors are connected one after the another, then we will call it this type of combination as series resistors. Now your resistor will have two ends. Okay, if you connect one end, okay, of the different resistors at one point, and the other end of the resistors connected to another point, then that type of connection, we call it that as parallel combination. Okay, in the case of series combination, there are some peculiar properties. Okay, now what are those peculiar properties? Let's try to see. In the case of series connection of resistors connecting one after the another, then in such type of series connection, what happen, same current will be flowing across different resistors. Okay, you have to note down this one. Same current will be flowing, whatever the current flowing here, that same current will also flow here, and also through this, across this artery also. Even though the opposition offered by these different resistors are different, it may have different value, but being connected in series, what happened, the current that is flowing, okay, when the circuit is completed, the current is flowing across R1, R2, R3, the current will remain same. got it? And the potential difference across these different resistors, okay, the sum of the potential difference across R1, across R2 and across R3, so this sum of the potential difference will be equal to the potential difference applied, okay. Whatever the potential difference here at the two ends will be equal to the sum of the potential difference. So let's take it that this is V1, V2 and V3, so that V1 plus V2 plus V3 will be equal to the potential difference between these two ends, one here and another here, okay. And the equivalent resistance, okay, or the resultant resistance. What is this equivalent or resultant resistance? If two or more resistors, if it can be replaced by a single resistor, then we call it that single resistor which will replace two or more resistor, we call it that as equivalent resistor of two or more given resistors, right? So the equivalent resistance in the case of series connection will be equal to what? The sum of the individual resistors. Suppose if your R is the equivalent resistors in connected in series, then this R will be equal to sum of the individual resistors. Suppose that R will be equal to what? Equivalent resistance. This will be equal to sum of R1 plus R2 plus R3 in this given figure, okay. So your equivalent resistance will be equal to what? Sum of the individual resistors. Now point to be noted is here, is that what happened? Your equivalent resistance will be greater than either of the individual resistors. Your R will be greater than R1, it will be greater than R2, it will be greater than R3 also. Got it? Those are the peculiar properties, okay. The first one is what? Same current flows through different resistors, okay. And what happened? The sum of the potential difference across different resistors will be equal to the potential difference across the two ends of those series connection, okay. One here, another here. That potential difference will be equal to potential difference across here plus potential difference across here plus potential difference across the last resistor, okay, like that. And equivalent resistance of these series connection will be equal to just the sum of the individual resistors, okay, R1 plus R2 plus R3. And lastly, what happened for series connection? The equivalent resistance will be greater than either of these individual resistors, okay. The opposite is in the case of what? Parallel combination of resistors. As I told you that a resistor has two ends. For this R1 you will have two ends like this. For this R2 also you will have two ends. So what happens if one end of the resistors, okay, different resistors are connected at one point, the other remaining points are connected to a one point, okay, another point, then that type of what? Combination or connection of resistor, we call it as what? Parallel combination or connection of resistors. So in this case, what happened? Same potential difference across different resistors, okay. This is the first special property or peculiar property, you can say. So what happened? Even though the resistance has its own resistance have different values for these resistors R1, R2, R3, what happened? Same potential difference will be there across these different resistors. The potential difference across R1, potential difference across R2, and that of R3 will have the same value, okay. So the first point is what? Same potential difference across different resistors will be there in the case of parallel connection. And the sum of the current flowing here, okay, across these different resistors. So let's take it that I1 is the current flowing through this resistor R1, I2 flowing across this what? Through this R2, and I3 be the current flowing through this R3. Then the sum of these currents I1 plus I2 plus I3, those currents flowing across these different resistors will be equal to the total current flowing in the circuit, Okay, suppose if current I1 is flowing here, okay, let the current I1 be flowing across this resistor R1, and let I2 be the current flowing here in this second resistor, okay, and let the current I3 be flowing here in this third resistor. Then what happened? The total current that is flowing across this conductor, that means let's take it that this is I, okay, so this total current I will be equal to what? The sum of these three currents. So it will be equal to I1 plus I2, okay, I2 and I3. So your total current will be equal to what? Sum of the currents flowing across these different branches of resistors. Okay, you can take it, this is first branch, second branch, third branch, like that. So total current will be equal to the sum of the currents that flows through different resistors, right? Yes, and the equivalent resistance of this parallel connection of resistors will be equal to what? It will be related by 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So you can remember like this: 1 by R, we call it this as reciprocal of R, right? 1 by R1 reciprocal of R1, 1 by R2 as reciprocal of R2, so on. Okay, so you can remember in this way. The equivalent resistance in the case of parallel connection and those of individual resistance can be connected as what? Reciprocal of the equivalent resistance. Okay, not equivalent resistance, mind you, this will be 1 by R, not capital R. Okay, so reciprocal of the equivalent resistance connected in parallel will be equal to sum of the reciprocals of those individual resistors. Okay, this is very important. And in the case of this parallel combination, what happened? Your equivalent resistance R is smaller than, okay, those individual resistors. Got it? Those individual resistors. That means your capital R here in the case of parallel, this R will be less than what? R will be less than that of R1, that of R2, or that of R3. So out of this R1, R2, R3, if R1 is the smallest one, then what happened? Your R will be also less than that smallest R1. Okay, less than, because your R is always less than either of these three resistors, R1, R2, R3. Okay, so the smallest one will be also what? Less than. This equivalent resistance will be less than the smallest one, right? That is what is to be noted. Okay, let's see for the next one. Let's try to learn about this EMF also. Okay, now EMF, what does this EMF represent? EMF means it is the abbreviation for electromotive force. It is also given here, electromotive force. Okay, what is this source of EMF? Now electromotive force, it is a pseudonym. The name has been given wrongly. Okay, if it is going to be a force, then this force will try to displace an object, okay, or an object's position, I mean. But this source of EMF will not displace the position of the conductor, or rather to anybody. Rather, this electromotive force means what happened? This source of EMF, like that of cell or battery, this will create the motion of those electrons, rather free electrons, present in the conductor. Okay, so some force seems to be given, okay, to those free electron present in the conductor, so that what happen, it will allow to have the motion of those free electrons in the conductors. So that's why we call it them as those dry cells, your battery, okay, source like that of applied source of electricity, we call it them as source of EMF. Okay, and what is this electromotive force EMF? rather your EMF is nothing but the maximum potential difference between the 2 points. Okay, 2 points. In the case of dry cell, it will be what? In the case of cell, I mean, it will be the two electrodes. Okay, in the case of battery, it will be that of positive terminal and a negative terminal, you can say. So, and in the case of some source of electricity, the two terminals, that will be the 2 points. Okay, so the maximum potential difference between those 2 points or two electrodes of the cell, when no current is drawn from the cell, we call it that maximum potential as simply EMF. Okay, so let's try to learn what is meant by what is the comparison between EMF and potential difference of a cell. Now, as I said in the definition, what happened, just to find out the EMF, then what happened, think of that an electric circuit is there with a source of EMF like cell and all, and what happened if your key is off. Okay, if your key is off, then what happened, no current will be flowing across, that circuit. Okay, suppose you are having, for example, say, let's take this as a cell. Okay, and a key here like this, and this circuit having a resistor like this. Got it? Now the potential difference that is going to measured, okay, here if you are having a voltmeter here, for example, if you are having a voltmeter measures what? Voltmeter will measure the potential difference across the two what points in a circuit, right? This is a cell, so this will represent what? Plus, and this will represent minus, and this will represent key, and this will represent your resistor, say capital R. Okay, external circuit. Got it? Now this voltmeter, when the key is open, okay, when the key is not closed, means open, then current will not flow through the external circuit. Got it? So the potential difference across the two ends of these cell, or two electrodes, or you can say the simply potential difference between the electrodes of a cell or a battery, when no current is drawn from it in the external circuit, we call it that potential difference as EMF. So the potential difference between the two electrodes of the cell or a battery, when no current is drawn from the cell itself, we call it that potential difference, okay, across these two electrodes, we call it simply that as EMF. Got it? When the current is drawn, suppose if K is closed, then current will be flowing here like this, right? In that case, the potential difference that is having in between these two electrodes, which is measured by the voltmeter, that will give you simply the potential difference of a cell. Are you clear? So let's see the comparison of EMF and the potential difference of a cell. EMF is the maximum potential difference between the two electrodes of the cell when no current is drawn from the cell. As I said, this is it as per the definition. When the current is drawn, then what happened? When the current is drawn, then what happened? The potential difference that is developed between the two ends of the electrodes, that will surely be less. And so what happened? The potential difference when current is drawn from the cell between two electrodes, I mean, we will call it that as potential difference of a cell. Got it? And EMF, it is independent. This is a comparison. Okay, the second point is what? It is independent of the resistance of the circuit. Whether this capital R, I mean in the external circuit, your EMF will be independent of this external resistor. Okay, why? Because when the current is off, when the key is open, then what happen? No current will be flowing. So irrespective of this resistance, okay, in the external circuit, your EMF will remain there. So it is independent of the resistance of the circuit, right? But in the case of potential difference of a cell, it will depend on this value how much opposition is offered to the flow of this current from the cell. Okay, it will depend on it, the value of the potential difference here. So the potential difference, okay, between two ends of the electrode, we call it simply as potential difference of a cell. So it will depends upon this resistance in the external circuit. That is what it is, proportional to the resistance between the given points. Okay, the term EMF is used only for the source of EMF. That means for the source of EMF, we will call it this potential difference as EMF. But if you are going to take the potential difference between the two electrodes, then we can't say that is a EMF across this R. We can't say in that way. So it will be always a potential difference in that case. Okay, so EMF is what valid, or we need to say only for the source of EMF, right? In the case of potential difference, it may be between any 2 points in the circuit, right? That is what it is mentioned. Now, as I told you that this is a maximum potential difference. So what happened? It is greater than the potential difference between any 2 points in the circuit. So in this circuit, what happened? This EMF will be the maximum potential difference, okay? And no other points, okay, no other 2 points in this circuit will have the same potential difference with that of the EMF. So EMF is a maximum, okay, potential difference, got it, between any 2 points in the circuit. However, in this case of potential difference of a cell is greater than the EMF, okay, of the cell when the cell is charging. Only when the cell is charging, in that case what happened, the potential difference between these two cells is greater than the EMF of the cell. Got it? Yes. Otherwise what happened, your EMF is always greater than the potential difference of a cell. Clear? Yes.